This is your presenter Asloob Mudassar, and I am presenting slide number 105 of the course on laser physics. Question is, electrical pumping is categorized as longitudinal and transverse. Discuss them briefly. Also discuss the excitation process occurring in the gas as laser material. The answer is, first we discuss electrical longitudinal pumping. This type of pumping is usually implemented for gas lasers. In this pumping, a continuous DC current or radio frequency current or frequency or current in pulsed mode is passed through the gas along the longitudinal direction to produce longitudinal discharge. A uniform current density in the laser tube will produce a uniform bluish glow of light, also known as glow discharge. An arc discharge, just like lightning, should be avoided during electric longitudinal pumping. A typical setup of electrical longitudinal pump is shown in figure 1. The caption of the figure is a typical electric longitudinal pumping system for gas discharge lasers. You can see that there is a tube, glass tube, having two sets of electrodes, one set on the left hand side, the other on the right hand side. Actually, this is a circular ring, electrodes in the form of a circular ring. So you can see two, actually this is one electrode in the form of circular ring, and this is another electrode in the form of circular ring, and these two, that is this set of electrode, this electrode and this electrode, they are connected through a voltage, through a DC voltage V0 and through a blast resistance RB, and the current flow through this one, and electric field is established from this electrode to this electrode. The rest of the procedure is explained in the next paragraph. A blast resistor RB is used to limit the current, or in other words, to stabilize the gas discharge at the glow position. The voltage versus the current characteristic of the curve of a gas discharge is shown in figure number 2. That is in this figure, where C is the desired operating voltage, which stays constant with a reasonable change in current. The caption of the figure is VI characteristic curve of a gas discharge and that of a DC power supply in dotted. So if we measure the voltage across a DC power supply, this dotted line corresponds to that one. That is the voltage across the battery, across the DC voltage supply, and the solid curve is actually the voltage across the electrodes. And you see that this we have plotted voltage versus the current, and the current is actually Vp, that is the peak voltage divided by the value of Rb. This DCS, DES stands for desired. So this V desired voltage is shown in the dotted line, horizontally shown. V0 is the maximum voltage supplied by the DC supply voltage. Vp is the peak voltage across the electrodes, and capital V is of course the voltage across the electrodes. So you see that when the value of Rb is very high, almost no current or zero current flows through the discharge tube, through the gas tube. Since no current flows, so if you measure the voltage across the battery, across the DC supply voltage, you will measure it to be equal to V0. So that's why at a value of a very small value, a very large value of the DC Rb value, When RB is very large, this Vp over RB is very small, so you are very close to zero. And here you will notice that the voltage across the supply is V naught, and this is the voltage across the DC supply. So when you increase the value, when you lower the value of RB, what will happen? The current starts flowing through the RB resistance, that is through the bias resistance, the current flows. So some of the voltage from this DC supply voltage will be dropped across the RB resistance. It means that the voltage across a DC supply will now be reduced. So if you keep on lowering the value of RB, you are allowing more current to flow through RB, and when more current will flow through RB, then of course the voltage across the bias resistance will increase, or ultimately you can say that the voltage across the DC supply would decrease. And this is what is shown in the dotted line over here. So if you lower the value of RB, that is you allow more current to pass through the circuit, then of course the voltage across the DC supply will keep on decreasing along this straight line following the ohmic law, and then of course it becomes zero when the whole voltage will be dropped across the bias resistance. Now what will happen across the voltage across the diodes? From this you can see that when the RB value is very high, it means that you are very close to this zero voltage value, and you can see that there is this solid peak will not has not yet started. But when you lower the value of RB, it means that you allow some current to pass through the bias resistance. It means that some voltage will be established across the diodes, across the electrodes. For example, from this electrode to this electrode, some voltage or some electric field will be established, and of course some current can flow through the glass tube, and you can measure the voltage across across the electrodes. So if you, for example, if you regard this as a positive electrode, you can regard this as a negative electrode or the ground electrode. So you can measure the voltage across these two electrodes. So when you keep on decreasing the value of RB, you are allowing more current to pass through the blast resistance, and you allow more current to pass through the laser tube. It means that you are applying more electric field across the voltage across the laser tube. So what will happen? The voltage will increase with the decrease in blast resistance, and it will reach a peak value Vp. So when you further reduce the value of blast resistance, what will happen? The voltage starts decreasing. So you keep on increasing the value, or you keep on decreasing the value of RB, and you will notice at this point that the current is also, that the voltage is also decreasing across the electrodes, because more current is now passing through the tube. So more current is passing through the tube. So here in this region you can see that the current becomes constant. That the current will increase at the constant voltage. No change in the voltage occurs now, and this is the desired voltage at which we want to obtain the lasing action. So voltage stays the constant, and the current can increase if you further lower the value of RB. So this is the operating region around the point C, is the operating region or the desirable region where we would prefer to operate the laser. And you know that there are 2 points we have shown, A and B. These are the 2 points which are highly unstable points, because a small change in the value of current will drastically increase the voltage along the point B, along the curve from point B, and along the curve from point A. A small change in the current will drastically change the value of voltage across the electrodes, and this is undesirable because the system will be highly unstable in this region. So you see that I have explained this curve, and this behavior is due to the discharge, is due to the gas within the discharge tube or within the laser tube. That is, initially when you lower the value of RB, the voltage starts keep on increasing. It reaches the peak value, and with further decrease in the value of RB, which means that you are allowing more current to pass through the glass resistance, which means that you are increasing the and then more current will also flow through the glass tube. So more current will flow, it means that the voltage across the electrodes will keep on decreasing. And when with further decrease in the RB value, more current will flows, and then you see that a stage will reaches when the voltage becomes constant and only the current can increase around the point C. This is the region around the point C, which is the highly stable region. That is with the small changes in the current through the discharge tube, the voltage is not changed and remains constant. So this dotted line is the desirable value of the voltage. So let me read this paragraph once again. A balanced resistor RB is used to limit the current, or in other words, to stabilize the gas discharge at the glow position. The voltage versus the current characteristic curve of a gas discharge is shown in figure number 2, the figure that I have just explained. C is the desired operating voltage, which stays constant with a reasonable change in current. Gas breakdown occurs only when the voltage across the electrodes approaches the peak value Vp, where in a typical case Vp, that is the peak voltage, is of the order of 10 times the desirable voltage. This is a typical, you know that the value. So if you find a peak voltage value, you can consider your desired voltage to be 10 times smaller than that, where DES is the desired operating voltage. Point A and point B correspond to an unstable equilibrium position, especially point B, because you know that a gas discharge, gas breakdown occurs only after the peak point, and after the peak point the curve goes over here. And you know that there is a point B lying at the intersection of this straight dotted curve and the solid curve. So this point B is actually corresponds to the unstable equilibrium position, because the point B occurs after the breakdown has occurred, and the point A occurs before the breakdown. So point A is not important, but the point B is important. But you know that the point B is unstable point, unstable equilibrium point, whereas point C is the stable and equilibrium point that is desirable. The dotted line in figure number 2, which I have explained also, shows the VI characteristic of the DC supply with a blast resistance RB in series. Different geometry of electrodes is possible for longitudinal pumping, but the electrodes in annular structures are most commonly used ones. You see that here this is an annular structure of the electrode. This is in the form of a ring around the tube. So this is in the form of ring around the tube, and this electrode is also in the form of a ring around the tube, which we can it as annular ring or annular electrode. For different geometry of electrodes is possible for longitudinal pumping, but the electrodes in annular structure are most commonly used ones. Large size of cathode is used to sustain impact of heavy ions and to cause less degradation of the electrode of the cathode to the surface. Longitudinal discharge setups are more suitable for continuous wave laser operations. Next, we are going to explain the electric transverse pumping. In this pumping, a continuous DC current or radio frequency current or current in pulsed mode is passed through a gas or a mixture of gases along a direction transverse to the resonator axis. to produce a transverse discharge. Transverse pumping produces a discharge which is relatively less uniform. So you see that this is one disadvantage of the transverse pumping, and less stable in comparison with the longitudinal pumping. So transverse pumping has two disadvantages. One is that it is difficult to produce uniform discharge, and the second is that it is less stable in comparison with the longitudinal pumping. The gas discharge theory in case of transverse pumping is the same as applicable to the longitudinal pumping, because the gas discharge or gas breakdown mechanism in both the longitudinal and the transverse pumping is the same. A typical setup of electric transverse pumping is shown in figure number 3. It is in this figure. You can see that there are two electrodes, one at the top, the other at the bottom, and there is a gas tube in between them, which I have not shown. So gas tube is lying between the two electrodes, with the horizontal of the gas tube is parallel to the electrode. So this is the transverse case, and you can again see that there is RB resistance, which is the load resistance, which is the blast resistance. V0 is the DC voltage supply, and in the dotted I have shown a capacitor, a blast capacitor in principle, which I shall explain after a minute. And you can see that the caption of the figure 3 is a typical electric transverse pumping system for gas discharge lasers with flat electrodes. You can see that the shape of these two electrodes are flat, but you know that sometimes these are usually curved in such a way that their focal point becomes the central point of the tube, that is the gas tube. So the gas tube is placed in between the two electrodes, and if these two electrodes are curved, then they are curved with such a curvature that they are focusing the point, their focusing point matches with the center of the tube. The surfaces of the electrodes must be very smooth and symmetric to avoid any discharge or arcing through the sharp corner or edges of the electrodes. Transverse mode of the pumping is useful for continuous wave, pulsed, or radio frequency lasers. In transverse radio frequency pumping, electrodes are located outside the discharge tube. So you see that here there is one advantage of the transverse radio frequency pumping. In that case, we can place the electrodes outside the gas tube. There are some advantages of that one that which will be explained in the next paragraph. So, but the transverse pumping, especially when we are using radio frequency pumping, is useful in the sense that the electrodes are lying outside the discharge tube. So you can see that in the dotted I have drawn a capacitor C, which is we can call it as a blast capacitor. In the sense we have called the resistor as the blast resistor. The role of this capacitor will be explained next. The tube glass thickness, because if we are using the electrodes outside the tube, then the tube glass thickness acts as a series of capacitors under radio frequency excitation and acts as an effective capacitive blast. So this becomes an effective capacitive blast rather than the resistive blast, which is shown in dotted in figure number 3. So in figure number 3, we have now the effective capacitive blast resistor. So this is the blast capacitor, you can say. The absence of the resistive blast thus avoids the loss of pump power. So you see that effectively we are producing the blast capacitor, and this avoids the pump loss, because if we are using in the sense of blast resistance, then of course there will be a lot of power dissipated through the blast resistor. but in case of a capacitor, this is not the case. So we can avoid a loss of pump power when we are using a ballast capacitor. The electrodes being located outside the discharge tube lessen the arcing problem also. So no arcing will occur when the electrodes are outside the glass tube. For example, in this figure you can see that there is a tube which we can call glass tube containing some gas over here, and there is a glass capillary tube through which the laser will come out from this end or from the other end, from this end, for example, because the glass capillary tube is not a continuous tube, but it is a tube that is shorter than the glass tube size. So the lasing process will occur in this tube and the laser will come out from this end, and you can see that the electrodes, that is the two electrodes, are outside the glass tube encapsulating the glass tube, and these two are highly parallel to each other. The gas is not in contact with the electrodes in this case, thus there is no dissociation of gas molecules. So you see that this is an advantage when our electrodes lies outside the tube, because there is no dissociation of gas molecules. This increases the life of the gas mixture as well as of that of the electrodes, because the electrodes also lies outside, so it will prolong the life of the electrodes. This curved electrodes, the curved electrodes located outside a glass tube are shown in figure number 4. So you see that here we have shown the transverse pumping case in which the electrodes lies outside lie outside the glass tube. And the caption of the figure is a typical electric transverse pumping system for gas discharge lasers with curved electrodes. Now a little bit about the excitation process. Now the excitation process occurring in a gas or a mixture of gases acting as a laser material is explained. In electric discharge, ions and electrons are produced. These ions and electrons are excited under the applied voltage, which we apply across the electrodes. Ions move with lower velocities being higher than the electrons, which move relatively faster. These collide, that is, the electrons collide with the neutral gas atoms and excite them. Ions' role in the excitation process is small compared with electrons. In a single species gas, let the name of that species of gas is represented by capital X. The excitation process leads to the following reaction shown in equation number 1. That is EH, that is the electron with higher kinetic energy, collides with the gas species X, and it raises and it excites the gas species which we have labeled as X star, which is an excited gas species, and plus we are left with the electrons with lower kinetic energy. So El is the same electron as EH electron, but El electron has lower in kinetic energy than with the EH electron, because EH electron during the excitation process have imparted some energy to the gas species X and has excited it to X star. Where EH is the electron with the higher kinetic energy before collision, and El is the same electron with lower kinetic energy after collision. Capital X is a gas atom in the ground state before collision, and X star is the same atom but in the excited state after collision. The reaction in equation number 1 is referred to as the collision of a first kind. So such a reaction that we have just described is called collision of first kind. If the gas mixture contains two species, let name them as capital X and capital Y, and capital X has a metastable level lying lying close to the desired excitation level of the Y atom. because the lasing process will be occurring in the Y atoms. Due to the Y atoms, then the following reaction in addition to the reaction 1 may occur. So the reaction 1 may occur, but in addition to the reaction 1 that I have just shown over here, for example, reaction 1 as shown in equation number 1 will also occur, but in addition to that one, reaction 2 will also occur. That is, we have the excited species X, which has a metastable state and a very long lifetime. It will interact, it will collide, or it will come in close proximity with the Y species, and due to slight collision between them, the Y gets excited, which we have shown as Y star, and X gives its energy to the Y star because the excited X has a energy which is very close to the level in Y, so it gives all its energy to the Y level, plus a small difference of energy is left, for example, which we have shown as delta E. So delta E is the small difference in energies between the X star species and the Y star species. So if X star species is greater than the Y star species in energy, then we can have plus delta E. And if X star species has an energy lower than the Y star energy, then we can have minus delta E, where the condition is that over delta E, that is the change in energy between the excited X star and the excited Y star should be less than the difference between these two excited states, delta E should be less than the KT, where KT is the thermal energy available in the environment. An excited metastable species X, that is X star, collides with the Y species and excites it, which contributes in the lasing process. That is, the Y species will have to contribute in the lasing process in this case. X will not contribute in the lasing process. For example, in the helium neon laser, helium is not contributing in the lasing process, only the neon will contribute in the lasing process. And the helium has a metastable state there, which has an energy very close to the energy of the excited states in the neon atom, which is used in the lasing process. Being capital X excited to the metastable state, that is X star, stays in the excited state for a long time. Collision of this type is known as collision of second kind. Collisions of first and second kind are the key processes involved in the excitation of atoms in a gas or in a mixture of gases acting as laser medium. So you see that I have explained in this presentation, I have given an account of the longitudinal excitation, longitudinal pumping, transverse pumping, and I have explained the excitation process that may occur in the form of collisions of first kind and collisions of second kind. These two collisions may occur mostly in general gas lasers. So this is the end of slide number 105.